All right, let's finish up this example here that we had from our notes yesterday. So we're just going to run through our different things and find all of our missing pieces. So first of all, let's start off with domain. So again, for domain, we look at our function and we say what can we not have, and we build the domain around that. So we can't have 0 because 0 causes a problem in the denominator, but everything else is okay. So we're going to say negative infinity up to 0. And then 0 to infinity. Next, x-intercepts. The x-intercept is where the function is equal to 0, so that's basically just where the numerator is 0. Excuse me. So whatever makes the numerator 0, which is just a 1, and again, remember this needs to be a point, so the point 1, 0. Y-intercept would be what we get when we plug 0 in for x. So if you plug 0 in for x, you get negative 1 over 0, which is undefined. So there is no y-intercept. Okay, so we're just going to say none. If there's no y-intercept, that means that there was a vertical asymptote on the y-axis. So that would be x equals 0. And again, make sure you have that as an equation of a line. Okay, so x equals 0. And again, that's just wherever we have a undefined, so 0 in the denominator for this one. For your horizontal asymptote, we look at our 3 cases with our highest power rule, or you could look at what happens if we take the limit as x approaches positive or negative infinity of this function, which is, it's the same thing you get if you look at your 3 cases. So if we have a bigger exponent on the denominator, that means that the horizontal asymptote was y equals 0. Okay, so vertical asymptote at x equals 0, horizontal asymptote at y equals 0. That tells us our end behavior. That tells us that this function, as we get really far out in the positive or negative direction, is approaching 0. It might be approaching 0 from above it, from the positive side, or below it from the negative side, but it is still approaching 0. Next, we found the critical points. So in order for us to find critical points, we need to find our first derivative. So let me just kind of section that off there. So first derivative. I would suggest you pause the video and try to do the first derivative yourself and then come back and check your answer. So go ahead and do that. Pause the video, try the first derivative, and see what you get. So when I did this, I did low x squared. The derivative of the top is 1 minus high x minus 1. D low, the derivative of the denominator, is 2x. Over the denominator squared is x to the 4th. And then I look at this and I say, okay, I have an x in all 3 of my terms. So this is a 3. This guy over here is gone. This is a 1. Now I'm ready to clean it up a little bit. So f prime of x is equal to x minus 2x plus 2. All of that is over x to the 3rd. Okay, so just cleaning up the numerator a little bit more here, negative x plus 2 all over x to the 3rd. All right, now we can find our critical points. So we know that we have a critical value, right? Our critical value here for this function would be at x equals 2, right? This is what makes this function 0 when x is 2. So our critical point, we just need to, plug that into the original function. Again, remember, anytime you're looking for a point, we're going to take that x value and plug it into the original to get the y value. So 2 minus 1 is 1, over 2 squared is 4. So this critical point is at 2, 1, 4th. Next, in our list, the next thing that we looked at was increasing and decreasing, determining whether this critical point was a max or a min. We'll do all of that in our table. And then we went on to our points of inflection. So to get our point of inflection, we need our second derivative. So same thing, I would suggest that you pause the video, take this first derivative right here, and see what you get when you take the derivative of that. get our second derivative. So I got low, x to the third. The derivative of the top is -1. Okay, don't forget about that. That's a common mistake there. Minus high, negative x. D low is 3x squared. All of this is over the denominator squared, so x to the sixth. And again, before I do anything else, I notice that the smallest power in each of these terms will be an x squared, so I'm going to cancel that out. X squared is gone. This will be an x to the fourth, and this will be x to the first. Okay, and if you have that, cancel it out, simplify it, make your life a lot easier so that it just makes your next steps a lot easier. So we end up with a negative x plus 3x minus 6. All of this is over x to the fourth. Clean it up one more step here. We end up with 2x minus 6 over x to the fourth. So what makes that 0? That's our point of inflection. That's the x-coordinate of our point of inflection, is whatever makes this 0. So that's a 3. Plug that into the original function. 3 minus 1 is 2. Over 3 squared is 9, so 2 over 9 is our point of inflection. All right, now we are going to take that value, see what happens around that to see, the concavity. Is it concave up, concave down? We're going to see what happens around our critical point to see whether it is a max or a min, whether it's increasing or decreasing. Another thing that we have to remember is, even though it's not a critical point, but we also had another critical value. I should have included that here. We had the one critical value at 2, but we also had another critical value at 0 because that is where the derivative was undefined. So we need to remember that when we're making our table. This 0 also needs to be included in our table. All right, so let's keep going here with our table now. And all right, so I have x values. Again, the x values that I need in my table are 0, 2, and 3, and then I need some numbers around them. So I need a number less than 0. Let's say -1, 0, a number between 0 and 2, so let's go with 1, 2, between 2 and 3, 2.5, 3, and then a number greater than 3, let's go with 5. Okay, so I know, well, let me, first of all, we're doing well, I guess technically a 3-row, but really 2 rows that we're filling in. We need the first derivative for increasing and decreasing and max and min, and the second derivative for concavity. I know that 0 wasn't undefined, so I'm just going to cross out that column. We don't really need to worry about that. 2 in my first derivative was a critical point, and 3 in my second derivative was my point of inflection. All right, so we need to see what happens to the rest of these values in our first and second derivative. And again, whatever happens anywhere in here, it happens everywhere. It only changes signs over the zeros and over your vertical asymptotes. So what happens when we plug in -1? Well, let me scroll up here. Negative x plus 2 over x cubed. If I plug a -1 in here, I get a positive on the numerator and a negative on the denominator. So that is a negative. I'm going to keep going with my first derivative here. If I plug in 1, if I plug 1 in here, I end up getting a positive on the numerator and a positive on the denominator. So that is a positive. Now I can choose any of these values, 2.5, 3, or 5. Take your pick. It doesn't really make a difference. If I pick 5, I end up with a -5 plus 2 is negative over positive is a negative. So since this one was negative, these are also negative. And if you don't believe me, plug them in and you'll see that you get the same thing, but you're doing extra work that you don't need to do. Okay, now I'm going to my second derivative right here. This is your second derivative, and I'm going to plug in these values to see what I get for concavity. -1. If I plug -1 in here, I get a negative over a positive. So that's a negative. Also keep in mind your denominator will always be positive here. So really all we need to look at is the numerator, okay? Because the denominator is always positive. So we don't really need to even look at the denominator. So 1, 2, or 2.5, I'm going to use 2 because I just feel like using 2. So 2 times 2 is 4 minus 6 is negative, so this is negative, which means that this was negative, and also this is negative. And then plug in a number bigger than 3, like 5. 2 times 5 is 10, minus 6 is a positive number, so everything after that is positive. So we end up with a table like this, okay? And again, just remember, we also have to include our vertical asymptotes because increasing and decreasing can change. Our concavity can change. It didn't change here, but it could change around the vertical asymptote, okay? It did not change. It was still concave down here, but it could change. So we have to include that to see what happens there. Okay, so now we're going to take all this information and we're going to put it all on the graph. All right, so let's see what we get here. Now I'm going to make because my y values are so small, like my critical point was 2 1/4, and my point of inflection was 3 2/9. I'm going to make this y-axis a little bit stretched out. So I'm going to say like right here is this is going to be 1, okay? We don't really even need to see anything above that, but anyway. Other than that, everything was at 0, 1, 0. Your x-intercept is 1, 0, so we'll put this here as 1. There was no y-intercept. Vertical and horizontal asymptotes are at 0, and then at critical points, the x value was at 2 1/4 and 3 2/9. Okay, so 1/4 and 2/9. And again, 1/4 is bigger than 2/9 because 2/9 is 0.2 repeating, like 0.22222, and 1/4, excuse me, 1/4 is 0.25. So just keep that in mind that our point at 2 will be slightly higher than our point at 3. Not much. We're talking about 0.03. It's not much higher, but it's slightly higher. Okay. So I'm going to do my asymptotes in red. So I have a vertical asymptote here at y equals 0. Again, I make them dotted lines because they're not part of my graph. And I have a horizontal asymptote at x equals, horizontal asymptote at y equals 0, vertical asymptote at x equals 0. My graph will be in blue. Now remember, your graph cannot, it's not allowed to cross over your vertical asymptote. Okay, that's not okay. Not allowed, can't do it, because that was an undefined. Horizontal asymptotes are just simply a guide. Okay, so our graph can cross over. It can cross over horizontal asymptotes. Okay, it can cross over horizontal asymptotes. Typically that happens at x-intercepts, like here at 1, 0. We have an x-intercept, and you can see our graph will cross there. It's going to cross there at that point, but it can never cross a vertical asymptote, so keep that in mind. So now, looking at our table, everything to the left of our vertical asymptote was concave down. So since we know it cannot cross the x-axis and it's concave down, meaning that it's going to have some kind of downward curve to it, hopefully you can recognize that this graph will look like this, okay? We only have two options, right? If it's not crossing the x-axis, it's either looking like that or it's looking like this. And that second one that I drew would be concave up, okay? So that part is not the graph. This is what our graph will look like. Also, if you plug a value less than 0 into the original function, you should see that we get a negative number. Like if we plug -2, we get a negative over a positive, which is negative. So that tells us that the entire graph is below the x-axis when we're out here to the left of 0. Okay, so let's see what happens here now between 0 and 1. Well, between 0 we can do this. So let's put our other points on the graph. 2 1/4, so let's say 2 1/4 is right here, somewhere in that area. And then 3 2/9, like I said, slightly, not much, but slightly lower than 2 1/4. Now, this is a point of inflection here at number 3 that is a very, very minor, is when we're looking at the graph, it's barely noticeable. Okay, but right here at 3, the graph changes, you can see in your table down here, from concave down to concave up. Now, this concave up is going to look like this. Very, very slightly noticeable. You may not even recognize it at all. Okay? And then everything to the left of 3 is going to look like this. Okay? So, again, I like to start at my points of inflection and go from there. So, starting here, I know that this graph is going to go, it has to go through 2, that's my highest point, has to go through 1, and then what happens here? Well, if this curved and went up, you see that would be concave up, and we would have to have, some value here that would show us that the second derivative was positive. And we didn't, it was negative. So this has to continue down. And then again, like I said, this value here, I'm going to try and make this look a little more noticeable. Let's say here's my value at 3. When this graph goes through 3, it's going to start to curve like that and flatten out to 0. So you can see there is a very slight upward curve, so it's concave up right here from 3 to infinity, where this over here was concave down. Okay, and again, you can look at that on your calculator. It's probably not going to be very noticeable at all on your calculator, and I would suggest maybe looking at it on like Desmos or something like that online would be much easier for you to scroll in and maybe be able to see that. But we know what's happening there because we did it in our table. So algebraically, we knew it was happening. But as far as the graph is concerned, sometimes it's not very easy to see what's happening there. Okay? So that is what your graph should look like for this second example. Now, what I would suggest you do is take this one and try it. Okay, so what I'm going to do is I will put the answers to all of these parts, the domain, x and y intercepts, vertical and horizontal asymptotes, critical points, point of inflection, and then show you the graph. I will put all that stuff on Google Classroom so you can see what it looks like, but I want you to try this one on your own, and then later on today I will put that information on Google Classroom and show you what I got. Keep in mind that your numerator does not factor nicely. So this is going to be one that you either have the option of completing the square, or it may be easier just for you to use the quadratic formula for that one. That's whatever you prefer. It doesn't really matter to get your x-intercepts, okay? So I just wanted to throw that little hint out there that this one's going to take a little bit more work for you to get the x-intercepts, okay? So go ahead and try that one and see what you get. And like I said, later on today I will put the answers on your Google Classroom.